Welcome back everyone. So in the last class we have seen our devices which will be used in our power electronics converter. Then we have seen the first type of our DC to DC converter which was in the non-isolated domain where we will not have any isolation between the source and your load. That was our buck converter where we have seen that it will be always generating voltage which will be output voltage will be less than the input voltage. So we say that to be a buck or step down converter. So this was our buck converter circuit. Okay, so we have seen how this converter was developed and we have considered the continuous conduction mode of operation of this converter. So what do we mean by continuous conduction mode? The inductor current over here, the current will be either positive or it can touch 0 for at the end of the cycle for one instant of time. Okay, so then we say that the inductor current is continuous or the buck converter is operated in continuous conduction mode. So when the switch was on, what was the operation of the circuit? The diode was getting reverse bias, so it was offering infinite resistance and the inductor was experiencing the voltage which are difference between your input and output voltage. Then when the switch was turned off, the inductor property is to maintain the current, so it was circulating the current in this direction and the diode was coming into conduction path, and this was the equivalent circuit when the switch was off. Then we have calculated the voltage across the inductor over the turn on time. Then we have calculated the voltage across the inductor when the switch is off. We have equated them and we have found out the relation between input and output, which is given as V0 or the output voltage is equal to duty ratio times of input voltage, where the duty ratio can be having any value between 0 and 1. So our output voltage will always be less than the input voltage. So that's why it is called a step down or a buck converter. So till now we were discussing continuous conduction mode. Okay, so we have also determined what will be the minimum inductor size required to maintain the continuous conduction mode. Suppose we have an inductor less than the critical inductance value or the minimum inductor required to maintain continuous conduction mode. So in that case, what will happen? Our inductor will not be able to maintain the current flow till the turn off time period. So this is true when the inductor has sufficient energy to force the current in this direction in the entire turn off time period. If that is not present, the inductor is getting discharged or its flux becomes 0. So it is having 0 magnetic energy, so it will not be able to force the current in this direction because in the second equivalent circuit the inductor was behaving as a load. Okay, so how we will say it is behaving as a load? The current in this stage, the voltage polarity will be plus over here, minus over here. In this case it will be plus over here and minus over here. The current is entering the positive terminal. Here if we see, the current is leaving the positive terminal. So in the case 2, it will be behaving as a source. Now the source is not having any energy to feed into the load circuit or to give any power. So what will happen in this case? The circuit will become inactive and it will return back to its normal state where there will be no current through the inductor path and the switch and diode will be carrying 0 current. So what changes will be there in the relation between your input and output voltage? What will be the behavior of the circuit when we have discontinuous conduction mode? That's what is shown over here. Okay, so if you see, when the switch was on, the voltage across the inductor is Vs minus Vo, that is the difference between input and output voltage. Now, till my inductor has energy, it will try to force the current through the output stage. So, this is the duration where we have assumed that inductor is discharging completely at D1 time instant. Okay. So, what will be the value of D1? Its measurement axis is shown from here. Okay. So, we are starting the 0 axis at the time when the switch was turned off and it is completed when my inductor is completely discharged or its flux is completely reset. Then in this case, during this time it will be experiencing a voltage of minus V naught. After that, my inductor is not having any energy, that is from D1t to the end of my cycle it is having 0 energy. So, there will be no current through the circuit will be ideal as it is. So, now the inductor current, if you see, it starts from 0 because it is discharging at every cycle and or it is getting reset to 0. So, it will start from 0, it will increase as it is experiencing a voltage V0 minus Vs minus V naught. So, it will be increasing till this point till the switch is open circuited. Then after that it gets discharged and it gets completely reset at this point, which is your D1t, this is your dt, this is my D1t where my inductor is completely getting reset. Similarly, the source current, when the source current is drawn in this case, when my switch is closed, the source current will be drawn. So, from 0 to t time, this will be my source current profile. During the turn off time period of the switch, there is 0 current drawn from the source. So now let us find out the relation between our input and output voltage by using the voltage across the inductor. So I know for steady state operation, PL will be, average PL should be equal to 0, or the voltage across the inductor over a cycle should be equal to 0. So now first for dt time, it is Vs minus V naught into dt. For the turn off time, it is minus V naught d1 by t divided by whole time period equal to 0. So if I solve this, I will find out the relation between my input and output given as d by 1 plus d1 into Vs. Okay. Now what has happened in this case? So will my output voltage be higher in this case or lower in this case compared to the previous one? If I see, d plus d1 is always less than 1. Why? If you see, the d1 duration is finishing over here. So d plus d1 is always less than 1. So this factor compared to d into Vs, which was in our CCM mode or the continuous conduction mode operation. So in this case, we have divided and factor which is less than 1. So obviously my output voltage will be higher when I go into discontinuous conduction mode. Okay. So what is discontinuous conduction mode? Does it mean that the load current will be discontinuous? No. Why? Because if I see the output stage, in my output stage I have an capacitor. Okay, so we have assumed the capacitor to be very high, or we are considering the capacitor size is sufficiently large such that when the inductor is not having any energy, it will be feeding the load. So load current is continuous. When I say discontinuous conduction mode, it is with respect to my inductor. Okay. So now coming back to the point which we have mentioned while discussing our inductor, that it will be used as an energy storing component. Okay, so if you see here, your inductor, role of inductor in this circuit, during this stage it is storing energy, during this case it is releasing energy. So here my inductor is behaving as an buffer energy storage element. So it stores the energy when my switch is closed, when it is open it is releasing the energy. So it is acting as a temporary storage of energy. Okay. So if my temporary storage of energy is not sufficiently large, so it will enter into the discontinuous conduction mode and we will have zero current for a finite duration of the cycle. If you see, we have zero current for the finite duration of the cycle. Then we say that the buck converter is operated in DCM mode. It is with respect to the storage element, that is inductor. It has nothing to do with the output current. Output current will be continuous because of the presence of capacitor. Okay, and we have also seen that the output voltage will be somewhat higher compared to the continuous conduction mode. Then what is the boundary of CCM and DCM, or continuous conduction mode and discontinuous conduction mode? It is given by D1. When my D1 becomes equal to the turn off time period, so I minimum will exactly touch 0 at the end of the cycle, then we say that it is at boundary of continuous conduction mode and discontinuous conduction mode. In this mode, still the analysis which we have carried for CCM mode of operation will be valid. After that point, if my duty ratio is becoming less than 1 minus d, we have to use the analysis which we have done for the discontinuous conduction mode. Now in the buck converter circuit, what was the relation between input and output? We have seen that it is always less than my input voltage. Suppose I want in an application that my output voltage should be somewhat higher than my input voltage. Okay, the solution for us is, the simplest solution is boost converter. Okay, so if you see here, again we have an inductor, we have a switch, diode, capacitor, the same elements but the arrangement is different. Now we have connected inductor in series with our source. We have an switch now which is connected in parallel with the series connection of your source voltage and the inductor, and we have a diode, we have capacitor at the output stage. Okay, so now this is again an example of second order system. Okay, so what is a second order system? So if I see the number of charge storing element, that are two, that is your inductor and capacitor. Okay, so now the order of the system is nothing but the number of charge storing element present inside the circuit. So in the previous case, in the boost converter or in the buck converter, we had one inductor and one capacitor as the charge storing element. So we have two charge storing elements. So we call that to be a second order circuit. Okay, so boost converter is another example of a second order circuit. Buck was our first example. Now what happens, or what is the operation of this circuit? When my switch is closed. Okay, so what will happen? We will see that. Before that, the assumptions. Okay, so again we are assuming that it is operated in steady state. So we have seen what is the meaning of steady state. The inductor current will start from every cycle at the same point, and the average inductor voltage will be 0, or when I see it in terms of the capacitor, average current through the capacitor will be 0, or the voltage will be starting from the same point at the start of every cycle. Inductor current is continuous. For the time being, we are assuming again the CCM mode of operation or continuous conduction mode of operation. Capacitor is very large, so that we are neglecting the ripple in the output voltage when we are calculating the parameters of the inductor. The switches are ideal. So here all the components are considered to be ideal. What happens when we have some type of nonlinearity, we will see at the end of this boost converter discussion. So here we are assuming that the turn on and turn off time of the switch is equal to 0, that is, it is instantaneously turning on whenever the gate is signal is provided, whenever the gate signal is removed it is turning off. Okay, the same set of assumptions we are carrying forward for the analysis. Now when the switch is closed, what will happen now? When I close this switch, what will happen to the diode? Will it be forward bias or not? Now I have closed the switch over here. Now the capacitor voltage will be plus over here. Then what is the voltage applied across the diode? If I see, it is getting reverse bias. So my diode will not come in the conduction path, because if it is experiencing an reverse voltage, okay, so or it is reverse bias. So my diode will be disconnected, and this will be the path of current. The from the source side it will just circulate through the inductor. For the load side, the capacitor will be feeding the energy into the load. Okay, so this will be the equivalent circuit when my switch is closed. The inductor is just charging as it is connected across the source. If I apply the KVL in this loop, in the loop 1 or the input loop, I will observe that VL will be equal to Vs, that is, the entire source voltage is applied across the inductor. Now it will be experiencing increment in the energy, because the current is entering the positive terminal. So it is behaving as a load, and it will start storing the energy. How much energy will be stored? Now we know the voltage of the inductor is given by L dI by dt. So now rearranging that with the same assumption that our switching frequency is very high. So I will replace the di by dt with delta I by delta t, where delta I is small change in the current by small change in the time. Now delta t, I know the value of delta t, it is equal to d into t, or the switch on time period. So my change in inductor current when the switch is closed is given by Vs by L dt. Now the complementary state of operation. Now inductor has stored the energy. It was, the current was flowing in this direction, and suddenly I have removed the gate pulse from this switch. So the moment I remove the gate pulse, what will the behavior of inductor? We know that it will try to maintain the current in this direction. In turn, it will bring this diode in the forward bias mode. Can the diode carry current in this direction? Yes, it is in the direction of arrow. So the diode can carry the current. So now the inductor will again start behaving as a source, and it will start feeding into the load. What is becoming in this case? Is the inductor sole source of energy in this case? No. The current through the inductor will be equal to the source current. So when the switch is off, in this case, both your source as well as your inductor are feeding the load. Okay. So in the buck converter, what was happening? When my switch was on, the inductor was storing energy. When the switch was off, the inductor was the sole source of energy, or inductor was responsible for feeding into the load. Whereas in this case, both my source as well as inductor are feeding into the load when my switch is disconnected or it is in the open condition. So if I find the relation between the voltage applied across the inductor and the input and output voltage by applying KVL, I will see that VL, or the inductor across the voltage across the inductor, will be equal to Vs minus V naught. Now VL is again given by L di by dt, because the voltage across the inductor will be always be equal to L di by dt, equal to Vs minus V naught. Now again with the same assumption that my switching frequency is very high, I will linearize the circuit and replace the di by dt by small change in current by small change in time, that is delta I by delta t. Then I know the turn off time period, it is equal to 1 minus d into t, that is the time duration for which my switch is off, and we are assuming the continuous conduction mode or in the CCM mode of operation. So here delta I L open will be equal to Vs minus V naught by L into 1 minus d into t. So now we have found out the current value or the change in inductor current when the switch was in the closed condition, and now we have determined what is the delta I L value when my switch is in the open condition. as we are assuming steady state operation, then in steady state operation delta IL or the net change in inductor current should be equal to 0. So, with the same assumption as we have done in the previous case, we will equalize both sum of your delta IL close plus delta IL open equal to 0. So, when I solve this equation, I will find out that V0 is given by Vs by 1 minus t. Okay. So, this is the relation between your input voltage and output voltage for a boost converter. Now, what is the value of duty ratio? It is always restricted between 0 and 1. Okay. So, if I replace any value between 0 and 1, I will observe that this will always be less than 1. Okay. So, and I am dividing Vs by an value which is less than 1. So, obviously my V naught will always be higher than Vs value. Okay. So, here in this case, in the boost converter, my output voltage will always be higher than the input voltage. So, that is why we say that to be a boost converter or a step up converter. Okay. Now, again assuming that it is a lossless circuit, so our input power will be equal to the output power. Okay. So, if you have loss in the circuit, the input power will be equal to output power plus losses. Now, we are considering the circuit to be ideal. So, the losses are 0. So, input power will be equal to output power. Now, I have replaced that input power and output power by Vs Is equal to V naught I naught, and I have derived the relation between the V naught and Vs. So, that is what I am replacing it over here. Then I will observe that Vs will be cancelled out. Now, I will find a relation between output and input current. Is is equal to I naught by 1 minus d. So, now it is an current buck converter. Why? If I see the output current, it will be equal to Is into 1 minus d. Okay. So, my output current is always less than the input current. Why? This factor is always less than 1. So, my output current will be less than the source current. So, this is a current buck converter circuit. Okay, or it is stepping down the current and increasing the voltage because my input and output power will be the same as we have neglected the loss in the circuit. Okay. Now, the graphs of various components. Now, what will be the voltage across the VL inductor voltage when the switch is closed? When the switch is closed, it was experiencing the entire source voltage. We have just calculated that. When the switch is in the open condition, it is experiencing a voltage which will be equal to Vs minus V naught. Okay, or the difference between your source and output voltage. In this case, will my inductor be charging or discharging? It should discharge because here in this case it was charging. So, how we can say that it is discharging in this case? If I observe Vs minus V naught, we have just found out the relation between an input output voltage, and we have seen that my source voltage will always be less than the output voltage. So, this will be always be a negative value. So, my inductor is experiencing negative voltage as shown in this graph also. So, it is experiencing negative voltage or it is behaving as a source. In this case, it is behaving as a load and stores the energy. In this case, it is behaving as a source and gets discharged. So, here again if I see, the inductor is used as a buffer energy storing element. Okay. So, in this case, the inductor stores the energy when the switch is closed. When it is in the open condition, it feeds the energy to the load and gets discharged. So, inductor plays the role of buffer energy storage component. Now, what will be the current through the inductor? Again, we have assumed the continuous conduction mode. So, it will always be finite and positive. It starts from the minimum current value. When the switch is closed, it experiences positive voltage across it, or it gets charged and it stores some energy. So, its current will be increasing. When the switch is off, it gets discharged and behaves as a low the source, and it gets discharged. So, this will be the current graph. It will be having a decrement in the current, or it is discharging. So, when I see the diode current, when my diode was carrying the current, when the switch was on or it was in the closed state, my diode was reverse bias or it was having infinite resistance, there was no current to the diode. When I opened the switch, the diode was coming in the path and it was carrying the current which was equal to the inductor current, because all these three components are in the series. So, they will carry the same component. So, here diode current will be same as that of inductor current, but the time duration is, it is limited only when the switch is in the off state or it is open circuited. So, dt to t, my diode current will be equal to the inductor current. Okay. Now, design of inductor. Okay. Suppose I want to find out what will be the minimum inductor required to continuous conduction mode, as we have done for the buck converter case. Here, now we will find out the value of delta IL Again we will find out the value of delta L minimum by using this delta L value and the average inductor current value, and we will be equating it to 0 to find out what will be the minimum inductor required, such that my IL minimum is just touching the 0 at the end of the cycle, or it is at the boundary of CCM and DCM mode of operation. That is what is the meaning of critical inductor. Then what is IL minimum? The average inductor current minus 50% of the ripple through it. Then note the average value of the inductor current is equal to the source current. Okay, so from where we have got this conclusion. Okay, so let us go back to our two equivalent circuits when the switch was open and closed. Okay, so if you see, this was the case when my switch was in the closed condition. Okay, so if I see the inductor current, what is that? It is again in series with my source. So it is the source current will be equal to the inductor current. Okay, now in the next case, here when the switch is in the open condition, there also if I see the switch and the source and your inductor are in series, again it is carrying the same current. So average inductor current over the cycle will be equal to the source current, because in both the equivalent circuit it is always coming in the series with my source. So this is what is the conclusion. How we have derived this? From both the equivalent circuit, if I observe the inductor connection, it is always coming in series with the source. So both for the positive and negative, that is for the charging and discharging duration when the switch is on or off, the inductor is always connected in series. So average inductor current will be equal to the average source current. That is what I will replace it over here. And average in our buck converter case, this average inductor current was equal to the average load current. Why? It was always coming, inductor was always coming in series with our output stage in our buck converter, whereas in this case it is always coming in series with our source voltage. Okay. So now IL is average inductor current is equal to the source current. Now replacing that, and we know that the relation between output and input current is also derived. Now the output current can be replaced as V0 by R, assuming that we have a resistive load at the output stage. Then we know the value of V naught in terms of your input voltage. So again we have replaced that, and we have found out the delta IL value. We are using the turn on case where it will be experiencing the source voltage entirely. We can replace it by the complementary condition also when the switch is off as per our requirement. So now if I equate it to 0 and solve it, I will find out that the minimum inductance value will be given by this relation, D into 1 minus D square into resistance, that is the load resistance, by 2 into your switching frequency. Okay. So if I am having an inductor greater than this value, my boost converter will operate in CCM mode. If it is less than that, it will go into the discontinuous conduction mode. Okay. Now the capacitor size. Okay. So now we have determined the inductor size. The other component which is left with us is our capacitor size. So how to determine the capacitor size? Again the same analysis. We will try to find out the current through the capacitor when the switch is in the closed state, and when the switch is in the open state. We can consider any one duration, or the charging period or the discharging period. In both the cases, equal amount of charge will be dumped into the capacitor, and in the other case equal amount of charge will be removed from the capacitor. Then only it will maintain the same voltage, or it will be going into the steady state operation mode. Okay. So in this case, so here it should be again like this. Okay, so we are just concentrating on the cycle 1. So in this case, what will be the delta Q value? That is the area under this current graph. So that will be delta Q is equal to C into delta V naught. So delta Q is equal to V naught by R into dt. From this graph, if I see, when the switch is closed, the entire source voltage was applied across the inductor, and the capacitor, what was happening to the output stage, the capacitor was feeding the entire load current. Okay. So the load current, it is nothing but V naught by R, that what was drawn from the capacitor. What is the duration for that? From 0 to dt time. So it is nothing but the area of this rectangle which we have obtained. So the height of that is V0 by R, and the base of that is dt. So just by multiplication both of this, I will be able to find out delta Q value. So if I replace that in this expression, I will see that capacitor will be given by V naught D into T by R into delta V0. Okay. Now relation between your input and output voltage we have already derived. So now in this boost converter, can I replace the duty ratio? Suppose I replace it by and value which is giving me an value which is nearly 0. Suppose I am considering the duty ratio to be 0.9. So, what will be the relation between input and output voltage in this case? 0.1. So, it will be 10 times Vs, or I will obtain an gain of 10 times. If my source voltage is 100, I will get an output voltage of 1000. And the second case, if I consider it to be 99, so what will be the value of output voltage? It should be 100 times of my Vs. Okay. So, can I set duty ratio setting to the high value, or this 1 minus d is set to a very low value? Can I get such high gain in the practical case? The answer is no. Why? We have a graph over here where we have just considered the practical circuit where it will be having some type of losses in the circuit. What are the losses? It can be the on-shift drop of our devices, it can be the loss of your diode, or it can be the resistance value of the inductor, or there will be a small resistance associated with the capacitor as well. So, when I consider these parasitics or the actual boost converter circuit, which our actual loss components, I will see that the relation between your output and input voltage with respect to duty ratio, it will follow our relation till end point, and after that it will start decreasing. What is the meaning of that? If I am increasing the duty ratio beyond 0.8 towards 1, ideally the gain or the output voltage to be continuously increasing, but in the practical scenario it will be falling. How it is so? We will see that by deriving the expressions. So, if I approximately tell the value over here, it will be around 3 to 4 times. Okay. So, after 3 to 4 times of my gain, that is what is the meaning of that? If I have an input voltage of 100, I can go up to and maximum of 400, or if I design the circuit with utmost care by using best quality devices and the components, so I can go up to 5 times. 3 to 4 times is the normal case. It can be reaching up to 5 times based on my design, but not beyond that. Okay. So, why it is happening? Why we are not able to achieve the infinite voltage when my duty ratio is nearby 1? It is because of my practical losses in the circuit which we have neglected while doing analysis for this converter. Okay. So, now for example, just let us consider that inductor is having a small resistance value. Okay. So, we are considering the every other component to be ideal, just we have relaxed our assumption with respect to the inductor, and we have considered it is having a small amount of resistance which will always be there. Okay. So, why this resistance would be coming into picture? How the inductors are constructed? By using your wires. Okay. So, the wire will have a small resistance, so which will be responsible for losses. Okay. So, now the input and output power relation. Okay. So, in the previous case when we are considering everything to be ideal, so my input power was equal to the source power was equal to the output power, but here it will be equal to output power plus a small amount of loss which will be created because of the resistance of the inductor. Okay. So, now this is Vs Is, V naught I naught, the input and output power. Now, we have an average inductor current, that is IL, and we have assumed the resistance of the inductor to be RL. So, I square into RL, that will be the loss or the power consumed by the resistance of the inductor. Okay. So, now we have now found out the relation between your source and the load current, that what is replaced over here. Now, this source current is nothing but equal to the average inductor current, that is what also we have discussed. So, now in this equation my IL will be getting cancelled out, I will be left with this simplified equation, and if I replace this IL, average inductor current, in terms of the output voltage, so I will find out this to be the relation, and the graph which we are seeing over here, that is obtained by using this relation. Okay. So, when I have a small resistance in the inductor, my relation between my input and output, this was my normal relation when there was no loss in the circuit, but when I consider the resistance loss of the inductor or the loss created by the resistance of the inductor, I have got an additional term. Okay. So, this, because of this additional term, there is a difference between the ideal characteristics and the actual characteristics or the practical characteristics. Okay. So, in our boost converter, the gain will be normally limited to 3 to 4 times. Okay. So, when I try to increase the gain beyond these parameters, because of the loss in the circuit, it will never be able to provide a gain which is beyond 4 to 5 times. Okay. Now, the next DC to DC converter. Okay. So, in this case we have buck boost converter. Okay. So, the name suggests it can operate in the buck mode or it can operate in the boost mode. Okay. So, now again what is the order of this circuit? If I see I have one capacitor, one inductor, in this circuit also. So, it is an second order circuit again, okay. And now if I see what is the change from the previous case, again the arrangement of my switch, diode and the 4 elements which are available with us, their positions are changed. So, now here in this case again proceeding with the same assumptions, that is we are operating in the steady state, inductor current is continuous, capacitor is large, these components are ideal and my switch is also ideal, that is it is turning on for dt time and it is turning off for 1 minus dt time, okay. When the switch is closed, what will happen to this converter? When I close the switch, okay, when the switch is closed, this terminal can my diode conduct now, okay. So, if I see the diode, it is getting connected to the positive of the supply, okay. So, when the switch is closed, so I can assume that this point is as good as connected to this point because we are considering the switch to be ideal. So, the positive terminal of supply is connected to the negative side of my diode, or the negative terminal of diode is connected to the positive of the supply. So, diode will get reverse bias and I will be left with this equivalent circuit where again the inductor is connected in series with the source and it is getting charged. On the output stage again my capacitor is feeding the load, okay. So, this is the equivalent circuit when my switch is in the closed condition. Now, again assuming the voltage values and applying KVL, my Vs will be equal to my inductor voltage because both of them are in parallel now. So, if I apply KVL in the input loop, I will find out that inductor voltage will be equal to the source voltage. Again with the same assumption, that is I am operating with an higher switching frequency, I will linearize the circuit and I will replace the di by dt as delta I by delta t. When I know the value of delta t, it is equal to dt. So, delta I by dt time it will be equal to Vs by L. Now, delta IL close will be equal to Vs by L into dt, okay. So, now coming back to the next state of operation, okay. So, in this buck boost circuit, now I have disconnected the switch, okay. So, if I disconnect the switch, what will happen now? The inductor, what was the current direction in the inductor? It was in this direction, okay. So, we know the behavior of inductor, it will not allow instantaneous change in current. So, it will try to maintain the current in this direction. So, what will be the path available with it? So, it can flow in this direction, yes. Why? The diode can carry current in this direction. So, it will be closing the path and your diode will be forward bias or it will be carrying the current, and this will be the equivalent circuit. If I see the diode has now started its conduction, or we are assuming the component to be ideal, now diode will be having zero loss in this case, or these two nodes will be connected with each other and this will be the state when my switch is in the closed condition. Now, VL will be equal to V naught. Now, the same analysis, now from the KVL, if I see if I apply it in this loop, I will observe that the voltage across the inductor will be equal to output voltage. Now, that will be given as LdA by dt, that is VL will be equal to LdA by dt. Then again with the same linearization, that is and the same assumption that my switching frequency is very high. So, I can replace the dA by dt as delta I by delta t. If I rearrange that and replace the delta t value by 1 minus d into t, the switch off time period. Now, delta IL open, that is the relation between the inductor current or the change in inductor current when the switch is open, and the output voltage will be given by this formula, okay. So, now we have found out what is the delta L value when the switch was in the closed state, when it is open in the open state. Now, we will equalize them to find out the relation between the input and output voltage. We know in the steady state the delta IL value or the average inductor current value should be 0, or it should start from the same point at the beginning of every cycle. So, if I add both of them, it should be equal to 0. By proceeding with the same relation, I will find out that my V0 will be equal to minus of d by 1 minus t, okay. So, now here we have gotten special sign that is negative. What is the meaning of that? Let us go back to the circuit. The meaning is, now here this will be the positive terminal, this will be the negative terminal of the output stage, or the capacitor will be charged to this and this polarity, right, in complementary to our assumption that it should be in this way, okay. So, that is what is the meaning of the negative side, its output voltage is inverted, or the positive terminal will be on the bottom side of the circuit, okay. Now, this duty ratio, okay. So, if you see the relation of your input and output voltage, what is the duty ratio term we have got? It is d by 1 minus d, okay. For buck converter we had only d, for our boost converter we had 1 by 1 minus d. In this case we have the combination of both of them, okay. So, if I replace any value between 0 to 0.5, Okay. So, if I replace any value between 0 to 0.5, I will get, and due to ratio what will be the outcome, suppose assume let us it is at 0.4. Okay. So, 0.4 by 0.6, that is what will be my Vs into Vs will be giving me the output voltage. So, it is 4 by 6 Vs. So, it is less than my input voltage. Now, the second case, suppose it is 0.6. So, due to ratio is equal to 0.6. Now, it will be equal to Vs into 0.6 by 0.4. So, again it is V naught is greater than Vs. Okay. So, what is the conclusion from these two examples? When my duty ratio is less than 0.5, it behaves in the buck mode. When it is greater than 0.5, it behaves in the boost mode. So, that is what is the name of the converter or justification for the name selected over here, buck boost converter. It can operate in both buck and boost mode of operations, and depending on the duty ratio. Okay. So, in conclusion, so we will continue from this point in the next lecture. So, here what we have discussed now. So, we have seen three different types of our second order DC to DC converter. First was our buck converter, which was operated in the step down mode, or the output voltage was always less than the input voltage. The second converter which we have seen was our boost converter, where the output voltage was always higher than the input voltage. Now, in the third converter which we have discussed is our buck boost converter, where it can have the output voltage less than the input voltage or greater than the input voltage, depending on the duty ratio which we set. Okay. So, we will continue from this point, and we will discuss further on our DC to DC converters. Thank you.